Hi, so welcome back to another video. In the last video lecture, if you're watching this in a series, we talked about kinematics in one dimensions, and we sort of introduced ourselves to things like position, displacement, velocity, and acceleration in a very preliminary understanding in one dimensions. And this time we're going to take it one step further and look at how all of these things work in 2 dimensions and even 3 dimensions, because in future lessons and concepts, we're going to have to apply more complex thinking in multiple dimensions. So let's get right into it. Again, we're going to be talking about position and displacement. So a general way of locating a particle is with a position vector, r with an arrow over it, which is basically a vector that extends from a certain reference point, which is usually the origin of an axis, to the particle in question. In unit vector notation, r can be written as x times I hat plus y times j hat plus z times k hat, where all of these are the vector components of r, and the x, y, and z coefficients are just these scalar components. And here we can see, for example, that here we have the origin on this graph, and we're looking at a 3-dimensional coordinate plane. And here, let's say we have the particle at this point, x, y, and z. So here is our vector r then. So it points into the 3-dimensional space. It has a z component over here. It has its y component over here. And then it also has a z component over here. So that's everything that makes up the vector r. And we should always remember that the vector position changes in a way such that the vector will always extend to the particle from the reference point or the origin. So for example, if the position vector changes from r1 to r2, then it would go through a displacement delta r, which would equal r2 minus r1. So the displacement would then become this equation right here, which can be written in the unit vector notation because we can subtract each one from its other component. And then this will give us this in unit vector notation. So moving on to velocity. We looked at average and instantaneous velocity before, but we're going to be looking at them as quantities, as vectors again, and using vector notation instead. So let's say a particle moves through a displacement delta r in a time interval delta t. So its average velocity, as we've discussed before, would just be its displacement over the change in time. So we've written it here in vector form. And this tells us that the direction of v average has the same direction as the displacement vector. So using the equation that we found on the previous slide, we can rewrite this equation for average velocity in its vector components. So here we've split it up into its different vector components in the x, y, and z direction. And this means that basically the velocity vector is just a combination of the velocity in the x, the y, and the z directions. And usually when we speak of the velocity of a particle, we usually mean the particle's instantaneous velocity at a certain instant in time. So this is simply the value that the average velocity would have if time approached 0. So if the change in time approached 0 about that instant. So if we look into calculus, we can simply use that and write the instantaneous velocity as a derivative, which is the derivative of the displacement or position with respect to time. So one thing that we should know is, say for example, we have this axis over here, And then we have a particle over here that's moving along some sort of curved line. So initially, let's say its position was here. So this would be, this position would be, let's just call it R1. But now it moves to this position over here, and that would be R2. So delta R in this case would be this line over here. Maybe I'll draw in another color for ease. So this line over here would be delta R. So that is the displacement. And we can see that as the particle moves, the position vector must change. And so basically when we shrink the time interval delta t to 0 about t1, so let's say that we want to find the instantaneous velocity of a particle at t1 when it was at r1. So t1 corresponds to r1. So we shrink the change in time to 0 about t1. So when we do that, the position vector r2 will move toward r1 so that delta r shrinks almost to 0. And therefore, the direction of delta r over delta t would approach the direction that is tangent to the particle's path at position 1. So that tells us that the direction of the instantaneous velocity of a particle is always tangent to the particle's path at that particle's position. The result is the same in 3 dimensions. The instantaneous velocity will always be tangent to the particle's path. And if we write the equation in unit vector form, we can substitute r, and this is what we get. So we can get the components of the instantaneous velocity, and the scalar components of v would just be these values right here. Okay, so now we've gone through instantaneous velocity, average velocity, and displacement in multiple dimensions. So we can look at average acceleration and instantaneous acceleration, which we looked at before, but now we're just going to apply some vector notation into it. So let's say that a particle's velocity changes from v initial to v final, v1 and v2, in a time interval delta t. Its average acceleration during this time interval would just be the change in velocity over the change in time, which we can write as this equation over here. Similarly, to find instantaneous acceleration or just acceleration, we can shrink that time interval to 0, or using calculus terms, we can take the limit as delta t goes to 0 about some instant, and then therefore our average velocity would just approach the instantaneous acceleration at that instant. So here we can see that the average acceleration is again just a derivative, this time of velocity over the change in time. And we can also take that as the second derivative of the displacement. So if velocity changes in either magnitude or direction, that means the particle must have an acceleration. So in the last video, we only considered a change in the velocity's magnitude, like let's say if it went from v0 to v. But now that we're looking in multiple dimensions, the fact that the direction of A relies on the direction of v means that a change in the direction of the velocity can also accelerate the particle, and we'll be looking at that in the next video. So we can also write the acceleration in unit vector form by substituting again for velocity to get this. And that just means that the components of the instantaneous acceleration are the components in the different directions. And this allows us to write it in a unit vector notation, where the scalar components are, again, these values in the x, y, and z directions. So to find the scalar components of A, we basically just differentiate the scalar components of v. However, when we draw acceleration vectors, for example, let's just take this object, for example, on the bottom right here. Let's just say that its acceleration vector is drawn like this. So this is the acceleration vector. The acceleration vector, it doesn't extend from one position to another. It just shows the direction of the acceleration for a particle located at its tail. And its length, which represents the magnitude of the acceleration, can be drawn to any scale. It doesn't have to extend from one position to another. And in this case, we have the acceleration vector A, and this would be the acceleration AX, the component in the x direction, and this would be a y in the y direction if we defined our axes to be x and y like so. Okay, so that was it for today's lecture. I hope you guys have learned something new. This one has gotten a little bit more complicated, and we're really getting into the nitty-gritty stuff of kinematics. I hope to see you guys in the next one, where we'll go over projectile motion and circular motion and look more into detail about the two-dimensional ways of looking at kinematics.